Hi. So we spoke about this lower dimensional data manifold. Let's now talk a little bit about this latent space and autoencoders. Really simple. So what we claim is that maybe understanding in general is like compression of knowledge. For example, we might go read a lot of stuff on the internet and then we somehow are able to say distill and compress all that knowledge and store it as some concepts in our head. Similarly, what we want to do is we want to, let's say, encode an image which has, let's say, about 800,000 pixels into these 128 numbers. And what we are assuming is that if we are then able to, let's say, reconstruct the image back from these 128 numbers, then maybe that is the understanding of the image, right? Maybe that is the low dimensional manifold that we were talking about. And then those 128 encoding numbers are then encoding concepts for us. Concepts such as maybe, the texture of the fur, the shape of the ear, the color of the eyes, and so on. And how we do it is really simple. In this case, we don't need any labels, so it's self-supervised or unsupervised, meaning we just need the images, right, which we can, or let's say images or speech or any of the data points without their corresponding labels. So we just need the image X, we don't need the Y. Okay, and then what we are saying is we don't need these images. We create this information bottleneck, meaning we are going down the dimension line, right? We are kind of going in this low dimensional space. We are projecting our high dimensional data point into this low dimensional latent space. Latent space is also called features. They're also called embedding, right? We'll use all these terms interchangeably. And finally, it learns from the data itself because there are no labels. And what happens is if the bottleneck is too large, the network almost becomes like a lookup table, right? So let's say if the bottleneck was as big as the size of the image, it can just cheat and copy the image over. And it is not forced to learn a representation, to learn, let's say, this latent space, to find that, lower dimensional manifold. So in that case, it kind of memorizes and it is not learning. So what do we do? Let's talk about autoencoders, right? What are these autoencoders? So autoencoders essentially are these encoder decoder pairs where the encoder essentially is this neural network which can just be, let's say, our linear layers, our fully connected layers with nonlinearity. Later they used, ReLUs and convolutions, and you can also use transformers. But the whole point is that you're going from this high dimensional, let's say, data where your, the manifestation of the data lives, where the image or the speech signal or your text paragraph lives, to this lower dimensional manifold, let's say these 128 numbers. So we are going from, say, 10 to the power 6 to this 128. So this is just one mapping. It's just a neural network where the output of that one layer is now these 128 numbers. And this is like I said, this Z is usually smaller than X. And why dimensionality reduction? Because if we don't have that, then it may not learn these, let's say, latent parameters. It may not learn where the data actually lives. It might just end up memorizing. So because we want the features to capture these meaningful factors of variation in our data, right? We want to kind of the elements of this vector, they should correspond to meaningful attributes such as, the ear, or let's say the texture of the fur, and so on. And then what are good properties of this embedding? So we'll talk about how to learn this embedding, but before we learn, what are good properties to have for this embedding? One, it should have mappability, meaning it should generalize, meaning new samples should map to valid points, right? Then the distance should be a measure of similarity. So if we take two of these z's, let's say we give it an image of cat1 and then we give it this image of cat2, and then it gives us these two z1 and z2 out. What we are saying is the z1 and z2, the Euclidean distance between them, right? So the Euclidean distance between them should essentially be a measure of the similarity. If the cats are alike, this distance should be low. If the cats are very different, then this distance should be high. It should be smooth, meaning we should be able to take this z1 and z2 and it should be we should be able to interpolate between them. If we have, let's say, different cats, very similar looking cats to very different looking cats, and we have, let's say, full gamut of it, if we have, them changing, let's say, in a smooth way, our interpolation should also produce these smooth transitions. And finally, invariance. So our embedding should be invariant to certain transformations of the image. It may be, let's say, a translation, rotation. So if we take the photo of the cat and we rotate it, maybe we don't want the latent representation to change because it's the photo of the same cat, and for this we want the same latent representation as output, the same z as output. So vanilla autoencoders don't guarantee any of these properties directly. We need better methods, but I'm putting it out there, right? Like, what is it that we are striving for? So how to learn this representation? How do we learn this z? We want this z, which is a lower dimensional representation of x, but how do we learn it? It's very simple. It's the simplest possible idea you can think of. What you want to do is, you want to train such that features can be used to reconstruct original data. In some sense, autoencoding, right? Encoding itself. Meaning, what you do is, you pass it this image of a cat, and as output, what you want, what you expect is, this image of a cat. And what we want them to be as similar as possible. How do we measure this similarity? The simplest way to measure this similarity is, let's say, our Euclidean distance, right? So what we are saying is, we have our input data, we put it into, let's say, this and then so we train this using our encoder decoder. So we have our encoder and we then have our decoder. So our decoder, so sorry, this is wrong, it should be encoder here and decoder here, right? So we have our encoder. The encoder basically does this downsampling and it gives us this z, and then this z, so our encoder lives here, right, and our decoder lives here, and the decoder then gives us images like these. And in this case, you see, they're not like perfect images, they're a little bit blurred because this averaging happens. But what we are trying to do is, we are wanting our x hat and x to be as similar as possible in some sense, in some measure. And one simple measure is our L2 loss function. So all we do is, we use this as our loss function, and we then say, okay, we have this one image as input, we put this image here as input, and here we want the same image. So we go to a lower dimensional, let's say this input image is of dimension 100 cross 100. So 100 cross 100 is 10,000 numbers, and from 10,000 we go to 128, and then we go back to 10,000, right? And then what we say is this, these 10,000 numbers and these 10,000 numbers, we do this L2 distance on, and we train our autoencoder in that sense. Though our output might look like this, not like this, right? Not like a crisp image. Our plane that we see here might, instead of this, it may look a little bit blurred like this. And this is because of the nature of our loss function, but we'll cover that later and how to kind of get over it. And GANs did that, and so many other models do that, but the autoencoder is unable to do that. So another thing to notice is, it doesn't use labels, right? All we need is the image, and the target is the full image itself. Yes, that is what we are computing the loss with. And after training, usually we may end up throwing this decoder, right? We don't need this decoder anymore. We throw it away and we only use the encoder, because our goal is to kind of create these embeddings, these latent vectors for our high dimensional data point. Our high dimensional data lives in this very high dimensional space, and we're trying to find that lower dimensional data manifold which is in a lower dimensional space, where each of these, like if you kind of are in this high dimensional space, then the pixels do not correspond to the semantic attributes. They don't correspond to the actual, let's say, axis of variability in our data. But we are expecting that our latent representation here, the latents are actually doing that. What you can do with these autoencoders is, so once you have your latent representation, you can do a bunch of things on this. You can maybe put a classifier on that, meaning you can multiply it, let's say, with a W matrix, and then you can, do, let's say, your classification in a simple way like we usually do. You can then maybe even fine train also the encoder. The feature extractor is also one of the names of the encoder, right? So this is something that you can do with the learned representation, because now learning, let's say, this will be easier because it will be a much smaller function, right? Because now we have these 128 numbers. So our vector here is 128, right? So it's 128 cross 1. And let's say finally we want to classify it, is it a cat or not a cat? So we need to get to 2 cross 1. And we can then multiply it with this matrix of size 2 cross 128, right, which has just these 2 rows. So our classifier here that we are learning, this classifier is then a very small matrix, and then it's easier to learn, it doesn't overfit, and all the good things. So this is one way you can use the learned representation. Now autoencoders can reconstruct data and can learn features to initialize a supervised model. Features capture factors of variation in training data. But the question is, can we generate new images using an autoencoder? The answer is no. This is because we throw away the decoder, and because we cannot sample in this space, we cannot just say, okay, give me a good Z. We know how to convert your X to a Z, but you're not able to just give me a random Z. If we perturb this Z, we may go outside that data manifold, and we will see later how do we then also sample from Z in something called as the variational autoencoder, and we'll talk about this variational autoencoder when we talk about GANs in our 7th week. Now there are 2 things to consider when we decide on the dimensionality of Z. Yeah, so we are saying Z is 128 is usually a good number, but what happens when we say our Z is just 2 numbers, right? We have our image of size 100 cross 100, which are these 10,000 pixels, and these 10,000 pixels we say we want to encode, so we use our encoder, and then we have our normal decoder, and at the decoder we again have our 100 cross 100, and we compute the L2 loss. Let's call this X, let's call this output X hat. We compute the L2 loss between X and X hat, and we learned this 2-dimensional Z. Now what can go wrong? We are compressing it too much. And what happens is, if the bottleneck is too tight, if the embedding is too small, then let's say, so then all information can collapse, because your network must learn to throw things away. So what it might do is, it might map wolf and dog to the exact same point. Let's say it maps it to, let's say, 3.2 and -6, image of a wolf and a dog, it might map it on to that exact same Z. Right? And that is not something that we want, because it doesn't have the bandwidth to encode the difference in the snout shape. Here we have a dog, and here we have, a wolf, and we are able to distinguish between the dog and a wolf because our representation in our head has that capability. We are not doing that collapse. If maybe some insect does that, because for an insect's evolution maybe a dog and wolf are same, but for us it's different, and so we have over time learned to represent it differently in our heads. So you lose that nuance and fine-grained distinctions disappear. The other problem that can have is this curse of dimensionality, meaning if this z that we were trying to learn, if this was too small, right, then we had that collapse. But instead of this 128, let's say we have a very high dimensional space, let's say 5000, right? So when you have this 5000, then again this curse of dimensionality hits us. And I'll not go to, this is like a very interesting thing to understand, but the message I want to leave you with is that in high dimensional spaces, we cannot really visualize higher dimensions, right? We can visualize 3D, we can maybe visualize 4D if we think of, let's say, time as a temporal dimension. So let's say, a movie, because we have frames of, let's say, so we can maybe think of a four-dimensional object, but anything higher is very difficult to kind of imagine. So there are two things I want to leave you with when we talk about high dimensions. High dimension is a very lonely place, meaning let's say we have 1D and we sample, let's say, 10 points here, right? So let's say we have 1D going from, let's say, 0 to 1 meters, and we sample 10 points randomly. So we get on an average a distance of, let's say, 0.1 meter between them. Now let's say we have 2D, right? We have now 2D, and now we want to sample the same, right? So if we now sample these points, their distance from each other will not be as less, right? So you see that the distance is increasing, and when you go to 3D, it gets more chance to kind of have that distance, right? So as you go to higher and higher dimensions, it gets really lonely. Most of the space is empty. These points, it becomes like this sea urchin. It becomes this very pointy space, and you can think of all these data points lying at those ends of the thorns of the sea urchin, right? It looks like a space like this, and extremely high dimensional space, Euclidean distance stops to make sense. It's very deep, but I don't want to talk about how. I just want you to give this intuitive understanding. There's also a lot of math behind it, but the intuitive understanding is because the space becomes like this sea urchin, and now the distance between all these data points is like this huge distance, and it's all the same. So points become roughly equidistant from each other, and this is why we don't want to go to that very high dimensional space, because now distances stop having meaning. And real life, we find that 128 to about 1024 is a good, let's say, dimension for us for this embedding space. Even when you go to, let's say, LLMs, your maximum dimension size is about 1024. So even these very large, let's say, trillion parameter models, or 500 million parameter models still encode that chunk of text, that 500,000 tokens of text, that 1 million tokens of text. The embedding is still this low dimensional, let's say 1024 sized vector. Yeah, so you don't have these very high dimensional latent spaces. You still have reasonably low dimensional latent spaces, because in high dimensions, each point is roughly equidistant to each other in the Euclidean sense. So that's all that we wanted to talk about. We wanted to talk about, how to learn this latent representations, and we don't need data to do it, because we have this encoder decoder. The encoder takes an image, the decoder then reconstruct this image. In the middle, we have that Z, which is the latent representation which we are actually interested in. And after outputting the image, we try to kind of compare the two images, the input and the output, and we say that they should be as similar to each other as possible. And we train this using, let's say, the Euclidean distance. After training it, we don't need the decoder, we can throw the decoder away, and then we can start encoding our images into these latent representations of size, say, 128. And then what do we do with this representation? Well, you can, for starters, train a small classifier on top of it. You can multiply it with your weight matrix of size 128 cross 2 and get those two classes out. You can train it with a cross entropy loss function if you want to train a classifier on top of your latent vector. You can also fine tune the entire encoder. So you can pass the gradients from your W, from your linear layer back into the encoder, and then it learns to extract better features more suited to this task. We call this a downstream task, this downstream classification task, and you know, our extractor, our encoder then becomes better at this downstream task of classification because we trained it so. Because the loss, the gradient from the loss of that cross entropy for classification, we passed it all the way to our encoder. And that's all that there is.